Hi, my name is Sarat, and in this talk, I will be presenting our work, NNK-Means, a data summarization approach from a dictionary learning perspective. First, let me motivate the problem and discuss what we mean by data summarization. In recent times, we come across large and growing amounts of data, which are one of the driving factors of progress in several machine learning systems. However, algorithms for understanding the structure of these large data sets, which is in general crucial for reliable learning and deployment of these models, have not scaled as much. Briefly put, data summarization is a small, compact representation of large datasets, analysis on which can help alleviate the scalability problem in data understanding. For example, consider a simple dataset as in figure. Given data, denoted by dots in the figure, that belong to a nonlinear manifold in data space, the goal is to learn a small set of elements, represented as stars in the slide, that can capture the characteristics of the data. In general, we want a few desirable properties in a data summary and the algorithm that is used to learn it. First, we would want the summary to be interpretable and along the input data manifold. Secondly, we would like to associate to each summary element data properties such as class labels, much like the input data itself. Finally, we want the algorithm to learn these summaries to be scalable and in general decoupled from downstream tasks. All right, let me present a one-slide overview of this talk. As we just discussed, the goal in this work is data summarization. In particular, we will make use of a dictionary learning setup where we will define the summary to be the dictionary learned. It is important to note that though dictionary learning is a very popular area, the idea of using a dictionary as a summary has not been previously studied. We believe one of the key challenges that prevented dictionary learning from being used in summarization is the fact that atoms in a typical dictionary learning approach does not belong to the data space. We propose NNK-Means, which involves a neighborhood-based sparse coding and dictionary update that allows for data summarization using dictionary learning. We show that NNK-Means learns summary elements that belong to the input space and are similar to kMeans cluster centers. Further, NNK-Mean produces a smooth partition of the input space, indicative of its ability to better capture the properties of the large data. And crucially, NNK-Means presents a desirable and scalable runtime with up to 67 times faster runtimes compared to a standard dictionary learning approach such as kSVD. All right, let me formally set up the problem. We will assume that similarities are captured in a transformed space via a kernel function, such as the Gaussian kernel, or an inner product kernel, which is equivalent to no transformation of the input data. Now, given data points represented in a transformed space as phi x in figure, the goal of summarization is to learn a small set D, represented in blue color in the slide, which is typically obtained by linear combination of the input data using a matrix A, where each data is represented or associated to this summary via the matrix W. The optimization problem, as in the slide, is solved by alternating between these matrices A and W. Now that we have formally defined the problem, let me discuss a dominant approach used for summarization, namely kMeans clustering. In this setup, the summary are the cluster centers, that is, the geometric centroid of all data that is associated to a cluster. The summary elements obtained via clustering are interpretable and do belong to the data space. Further, each cluster center can be associated to data properties, such as a software version of class label. Note that in this setup, solving for the representation or reconstruction matrix W is based on nearest neighbor search and is very fast. For completeness, we will describe the two steps in the algorithm. First, assign each data to its nearest cluster center. In our setup, this assignment corresponds to each column of W being associated with a one sparse vector. Second, update the cluster centers via weighted averaging. This step corresponds to assigning averaging weights in the matrix A. The algorithm iterates between this one sparse coding and cluster update to learn the centers of the clusters. A problem with this setup when being used in data summarization is the restrictive constraint of one sparse representation. This limitation was previously observed in a different problem setup and motivated the field of dictionary learning and approaches such as kSVD and method of optimal direction. The key idea in these dictionary learning approaches is to replace the one sparse coding in kMeans and represent each data as a sparse combination of the dictionary elements, with sparsity constraint generally greater than or equal to 1. Formally, a dictionary learning algorithm iterates between sparse coding, generally solved via iterative thresholding or L1 norm constraint optimization, and a dictionary update where one resorts to a least square solution as an MOD, or a singular value decomposition based on residuals as in kSVD. However, this setup does not allow for dictionary use for summarization. First off, yes, the representation obtained via dictionary learning is better than kMeans, but this comes at the cost of increased runtime. The atoms learned are designed to represent the data as well as its residuals, and thus need not belong to the input data space. The sparse coding lacks geometric interpretability as in kMeans, and the resulting atoms cannot be associated with data properties. Let us now look at a visual example of the key differences between a kMeans approach and various versions of dictionary learning approach. Here we consider a digit dataset, namely NNist, which consists of 60K points, and learn a dictionary of size 100. The first plot from the left shows the kMeans center. The second shows a standard unconstrained dictionary learning approach. As alluded earlier, the atoms here represent data and its residuals, and hence most atoms do not look anything like the input data. The third and the fourth plot correspond to constrained version of the dictionary learning, which we enforce on the matrix, namely matrices W and A, during optimization. Here we see that with a non-negative W, we do learn atoms that look more like digits, however, without any explicit geometry or interpretability. Bottom line, dictionary learning provides better representation of data compared to kMeans, but lacks important properties that makes it usable in data summarization. The last plot corresponding to our method, which we'll introduce next, shows similarity to kMeans in terms of atoms learned, while corresponding to better representation of the input data. The key idea we propose in a dictionary learning setup to achieve summarization is to replace the sparse coding component to a setup similar to kMeans using neighborhood-based approach. First off, note that this approach improves the runtime, as now the coding is just a nearest neighbor search, and also allows for better interpretability of the representation. A naive approach to this idea would be to use k nearest neighbors instead of one nearest neighbor used in kMeans. But this leads to a very ad hoc and redundant representation where we can have multiple points from same direction in the data space. This is problematic as the suboptimality in the representation leads to unstable optimization corresponding to the dictionary update. As a solution, we make use of a recently introduced neighborhood representation method, the non-negative kernel regression, or NNK. At a very high level, NNK corresponds to a sparse representation based on hyperplanes where each query is surrounded by a polytope neighborhood. As shown in the figure, this is in contrast to a KNN approach where neighborhoods are considered to be hyperspheres, where points within a radius which is defined using the choice of K are considered neighbors. Consequently, NNK neighborhoods are more robust to parameters such as K, where a KNN geometry is defined entirely based on the choice of this parameter K. Note that with NNK, we have explicit sparse representation geometry, much similar to the nearest neighbor assignment in kMeans. With that, let me introduce our algorithm, NNK-Means. As with previous methods, the algorithm consists of two steps, sparse coding and dictionary update. The key novelty in our method is in the sparse coding step, where we replace a non-interpretable and optimization-based sparse representation with an optimal neighborhood-based positive sparse coding, the NNK. The dictionary update in our approach makes use of a simple least square solution, as in the method of optimal directions. But now, with the geometry encoded in the sparse coding, we can analyze this step geometrically as well. NNK-Means learns atoms that belong to the data space and can be individually associated to properties such as class label. The figure shown here again presents a visual validation of this. To emphasize the name of our approach, consider the situation as in the figure on the right. A kMeans approach associates a data point using its nearest neighbor. In contrast, NNK solves to represent this data using a polytope around this data point formed by the nearest dictionary atoms. This geometry is in general absent in sparse coding previously used for dictionary learning. The table on the right outlines the key similarities and differences between NNK-Means with that of linear and kernelized versions of kMeans and kSVD. In general, a kMeans approach has non-negativity in its representation and geometric interpretability, but is restrictive. A standard kSVD dictionary learning approach achieves better representation, but lacks non-negativity in representation and geometry. Proposed NNK-Means is geometric with non-negativity in the sparse assignment with an adaptive sparsity defined based on the local position of the dictionary atoms. We show in our paper that theoretically, NNK-Means converges at a rate similar to kMeans, and that it reduces exactly to kMeans when the sparsity of representation is constrained to 1. We direct the reader to our paper for further details on this. All right, now we will validate the representation ability of NNK-Means experimentally. To be comparable with dictionary learning approach, we consider a per class summarization and then classification using the obtained summary. Each approach learns 10 atoms per class and is optimized with maximum sparsity of 5 where applicable and for 10 iteration. We will use a Gaussian kernel with sigma 1 in all our experiments. The plot in the slide shows the obtained class partition using different approaches on a 4-class dataset as shown in the first plot from the left. Each color corresponds to a class in the plot. We see that in plots 2 and 3, a kMeans approach is able to adapt to the geometry of each class data, but leads to a hard, non-smooth partition due to the one-sparse restriction in its representation. Fourth figure corresponds to a linear kSVD, and we see that it is unable to account for the nonlinear structure of the input data. This problem is alleviated by the use of a kernel in this kSVD approach, as can be seen in figure 5, but this comes at the cost of poor scalability. Finally, our approach, NNK-Means, corresponding to the rightmost figure, shows adaptability to the structure of the data and achieves a better smooth partition of the data while having a runtime similar to kMeans. In this slide, we present the performance of our method in comparison to baseline methods we listed previously using a real-world dataset, namely USPS digits data. Here, we learn per class summarization with maximum sparsity of 30 and optimized for 10 iterations with a Gaussian kernel where applicable. The plots in the slide presents number of atoms per class learned on the x-axis and reports the test accuracy on the left figure with training time and test time on the middle and right figures respectively. NNK-Means is denoted using the black line in figure. We see that NNK-Means achieves better performance than the baseline while having a training time similar to kMeans approach, denoted in blue and orange. Also, we note from the figures on the middle and right the poor runtime of kernel kSVD, denoted in purple, and a kSVD approach, denoted in yellow. We note that the runtime of kSVD approaches are at least 67 times worse compared to NNK-Means in training and 7 times worse during testing or inference. Bottom line, proposed NNK-Means achieves better test performance than the baseline methods while having a desirable runtime for training and inference. We refer the reader to a paper for more experimental results where we show that NNK-Means performs other methods in datasets such as MNIST and CIFAR-10. To conclude, we saw that data summarization is an important problem, crucial for the understanding of the structure of modern large datasets. A proposed NNK-Means algorithm presents a dictionary learning approach to summarization, where the learned summary corresponds to better representation and has adaptive sparsity. NNK-Means is geometric like kMeans with summary elements that belong to the data space, unlike previous dictionary learning approaches. Further, the runtime of NNK-Means is scalable and can leverage advances in approximate nearest neighbor tools to scale even further. The MATLAB and Python source code for both NNK and NNK-Means is available at our StackUSC GitHub repository. We will be happy to answer your questions and discuss via email. Thank you for your time.